Hello everyone and welcome to Lecture 16 of 124-103 Biophysical Principles. In this lecture, we will learn about heat. At the end of this lecture, you should be able to describe and explain heat and specific heat capacity, use specific heat capacity to solve problems involving a change in temperature, describe and explain latent heat, use latent heat to solve problems involving phase change. And in some problems, we will combine specific heat and latent heat to look at some scenarios where there is a combination of a change in temperature and a phase change. So, what is heat? Before we answer that, let's review temperature from lecture 15. In the previous lecture, we learned that temperature measures how hot or cold an object is. Now, if two objects that have different temperatures are brought in contact with each other, such as this cold ice and this hot liquid, energy will be transferred from the hot object to the cold object. The arrow tells us the direction of energy transfer, and energy is transferred from the high temperature object to the low temperature object until both objects have the same temperature. When the two objects have the same temperature, energy is no longer transferred, and then we say that these two objects are in thermal equilibrium. Heat is therefore defined as the transfer of energy across a boundary because of a difference in temperature. Without a difference in temperature, energy is not transferred between objects. And heat is transferred from a high temperature object to a low temperature object, and this transfer only occurs until thermal equilibrium is reached, meaning until the two substances have the same temperature. The term heat is also used to represent the amount of energy transferred. So heat is also used to quantify how much energy is transferred from the hot object to the cold object. The SI unit for heat is the joule, or capital J. Another unit for heat is the calorie, with a small or lowercase c. Calorie can be converted to joule using this conversion factor. 1 calorie with a lowercase c is equal to 4.186 joules. Now, why the emphasis on lowercase c? It is because calorie with a capital C means 1,000 calories with a lowercase c. So 1 calorie with a capital C is equal to 1,000 calories with a small c. Therefore, 1 calorie with a capital C is equal to 1 kilocalorie with a small c, and that is equal to 4.186 kilojoules. Recall that the prefix kilo is equal to 10 to the 3 or 1,000. Okay, so when heat is transferred from a hot object to a cold object, temperature will change. And the amount of heat needed to change the temperature of a material having a mass m by a temperature delta T is given by this equation. Here, Q is the amount of heat transferred from the hot object to the cold object. Okay, and this heat Q is measured in joules. M is the mass of the object whose temperature changes. Okay, and the mass is given in units of kilograms. SI base unit for mass is kilograms. Delta T is the change in temperature. And the change in temperature is defined as the final temperature minus the initial temperature. Now for the units of delta T can either be in degrees Celsius or Kelvin. We've seen in the previous lecture, in lecture 15, that when we are taking the change in temperature delta T, then degrees Celsius will be equal to Kelvin, meaning the change in temperature given in degrees Celsius will be equal to the change in temperature given in Kelvin. To know which of these two units you need to use appropriately, we will have to look at the unit of C. So C here, C is a property of the material called the specific heat capacity. Specific heat capacity. Or sometimes C is simply called specific heat. Okay, let's talk more about specific heat capacity or specific heat C. The specific heat C is a measure of how much energy is needed to change the temperature of 1 kilogram of a substance by 1 degree Celsius. And the unit for specific heat is either given as joules per kilogram per Kelvin or joules per kilogram per degree Celsius. So going back to the unit for delta T, change in temperature, the tip I would give you to determine whether you should use kelvins or degrees Celsius for the unit of change in temperature is to look at the unit of the specific heat capacity that is usually given or that you can usually look up in a table. So if the specific heat capacity was given in units of joules per kilogram per Kelvin, okay, then your change in temperature should be given in Kelvin. And if the specific heat capacity is given in units of degrees Celsius to the -1, then your unit for change in temperature should be given in degrees Celsius, so that we have consistent units all throughout the equation for Q is equal to mc delta T. Okay, so specific heat measures how much energy is needed to change the temperature. So we can think of specific heat as thermal inertia, or the resistance of a substance to change in its temperature. Therefore, the lower the specific heat, the lower the resistance to a temperature change, and the easier it is to change the temperature. As mentioned earlier, specific heat is a property of the material. So you can look it up from a table, okay, such as this table given in this slide. So again, if you look at the units, specific heat can either be given in degrees Celsius or degrees Celsius or Kelvin. In this table, you can pick out a specific heat in terms of degrees Celsius. So if you use any of these numbers for specific heat, then the unit for your change in temperature should be in degrees Celsius. And you can also see here that the unit for your heat, Q, should be in joules, so that it's consistent to the unit of specific heat, which is in joules. And the unit for your mass, M, should be given in kilograms, so that it's again consistent to the unit in the specific heat, which is given in kilograms. Look at this scenario and figure out whether iron or silver has a lower specific heat. It takes about 2 minutes to raise the temperature of an iron pot of water to boiling temperature. On the other hand, it takes less than 1 minute to raise the temperature of the same quantity of water in a silver pot to boiling temperature. Which one will have a lower specific heat capacity, iron or silver? So recall, the specific heat is a measure of thermal inertia. Again, the higher the specific heat, the more difficult it is to change temperature. So therefore, in this case, in this scenario, silver has a lower specific heat capacity because it took faster to change its temperature. In fact, if we look up in a table the specific heat capacities of silver and iron, we'll see that the specific heat capacity of silver is 0.23 kilojoules per kilogram Kelvin, while for iron, its specific heat capacity is 0.45 kilojoules per kilogram Kelvin. So indeed, silver has a lower specific heat capacity. This example shows that different substances have different specific heat capacities. It's a unique property of a substance. Look at this scenario and figure out whether water or iron has a higher specific heat capacity. 1 gram of water requires 1 calorie of energy to raise the temperature by 1 degree Celsius. On the other hand, 1 gram of iron requires 1/8 as much energy for the same temperature increase. Therefore, water absorbs more heat than iron for the same change in temperature. Which has a higher specific heat, water or iron? If you answered water, then you are correct, because water has a higher specific heat because it took more energy to increase its temperature compared to iron, meaning water has a higher resistance to changes in temperature. Therefore, it requires more energy to change its temperature, and therefore it has a higher specific heat. This example shows that equal masses of different materials require different quantities of heat to change their temperatures by a specified number of degrees. Now let's look at another example. This time, let's look at a numerical example where we will calculate how much heat is transferred. So the scenario is 30 grams of mercury is cooled from 200 Kelvin to 100 Kelvin. The specific heat capacity of mercury is 140 joules per kilogram per Kelvin. And we are asked to calculate how much heat is transferred in order to achieve this change in temperature. So again, as with any worded problem, it's useful to write down what's given in the problem. So we are given the mass of mercury, the substance whose temperature changes, and that's 30 grams. Okay. Don't forget to convert your units to SI base units, meaning convert grams to kilograms by dividing by 1,000. So that will be 0.030 kilograms, corresponding to 30 grams. We're given the initial temperature, which I'll just indicate as Ti. Okay. So I stands for initial. So the initial temperature is 280 Kelvin. We're given the final temperature Tf, which I write as Tf. F stands for final. And the final temperature is given as 100 Kelvin. From these two temperatures, we can find the change in temperature delta T. Okay. Delta T is final temperature minus initial temperature. Okay. So notice your final temperature is lower compared to your initial temperature. So your change in temperature delta T will be 100 Kelvin minus 200 Kelvin. That will give you a negative 180 Kelvin. And we are given the specific heat capacity C for mercury. It's 140 joules per kilogram per Kelvin. Okay, so now we are being asked to calculate how much heat is transferred, meaning we need to find Q. Q is the amount of heat that's transferred from a hot object to a cold object. Okay, so we've seen earlier in the previous slide that Q, the amount of heat needed to change a temperature of an object, is equal to mc delta T. Okay. And we have everything that we need to solve this equation. Mass is 0.030 kilograms. Specific heat C is 140 joules per kilogram Kelvin. Okay. And delta T, change in temperature, we solved earlier as negative 100 Kelvin. Okay. So let me just focus your attention for a while on the units here. So we should be consistent with units when we are solving a problem. So this kilogram here will cancel with that kilogram there. This Kelvin in the change in temperature will cancel with the Kelvin unit in specific heat. So we are now left with the unit of joules for the energy. So plugging in the numbers in your calculator, you will find Q to be negative 756 joules. Okay. Right, so the unit joules came from here, and that's the SI base unit for Q, the amount of heat transferred. Now you can see here that there's a negative sign. Okay. So this negative sign means that heat is taken out of the object. And since heat is taken out of the object, that means that that object, the mercury, cooled down, and that's why its final temperature is less than its initial temperature. So here you can see that Q, the amount of heat transferred, can either be positive or negative. If Q is positive, if Q is positive, the sign of Q is positive, it means that heat is added to the object. And if heat is added to the object, that means the temperature of the object will increase. And so you'll find that the final temperature of that object should be greater than the initial temperature of that object. Okay, now sometimes when heat is added to a substance, the phase of that substance will change. Okay. When we say phase, it's the state for which the object exists. And there are three major phases where an object can exist. The object can either be solid, liquid, or gas. Actually, there's a fourth phase called plasma, but we will not talk about plasma in this course. So we will only consider these three phases: solid, liquid, and gas. And when we say phase change, we mean that the object state can change from solid to liquid, for example, and liquid to gas. So as an example, if the phase change where solid changes to liquid is called melting. Okay? And when liquid changes to gas, that process is called evaporation. When gas changes to solid, that process is called deposition. And we can also have the reverse phase change, so that solid can turn into gas, and that phase change process is called sublimation. Gas can turn to liquid, and that phase change is called condensation. And liquid can turn to solid, and that phase change is called freezing. So naturally, when an object undergoes phase change, heat is needed to change its phase. A very good example of that is when you boil water. You are converting liquid to gas. So there's a phase change from liquid to gas. And in order for you to boil water and to achieve this phase change from liquid to gas, you need to input some energy in water for it to boil. So naturally, we'll see that heat is needed for an object to undergo phase change. Okay. In other words, to change the phase of a substance from solid to liquid or liquid to gas, for example, extra heat energy is required. This is because the bonds in the material need to be broken in order for phase change to occur. And the energy required to change the phase is given by this equation. Q is equal to plus minus ml. So what does this plus minus mean in front of ml? So let me define the variables first. So Q is as what we've seen before. This is the heat needed to allow the material to undergo phase change. And again, it's measured in units of joules. M is the mass of the material or the object that is undergoing phase change. And mass is measured in units of kilogram. And L is a quantity that we call latent heat. So latent heat, we'll talk more about latent heat in the next slide, but it's also a property of the material, just like specific heat capacity. And the unit for latent heat, just looking at the units for Q, which is joules here, and the unit for mass, which is kilograms there, the unit for latent heat will be joules per kilogram. Okay, now back to this plus minus sign in front of ml. So that just means that you can write down this equation Q in two forms. So it's either Q is equal to plus ml, or the second form Q is equal to minus ml. Okay. So in the first form, Q is equal to plus ml. The positive sign here means that heat is being added to the material. So for example, that will be liquid water boiling and changing phase into steam or gas phase of water. So you need to add energy to liquid water in order for liquid water to be converted to gaseous water or steam. In the second form, Q is equal to negative ml. Negative here means that energy is taken out of the object or of the material so that it undergoes a phase change. So an example here will be freezing of water. So when water is frozen, we're actually taking out energy, and the temperature of water decreases, and that corresponds to this negative sign here. The transfer of energy is out of the material or taken out of the object. Okay, now let's talk about latent heat in more detail. Okay. So latent heat, as we've seen in this equation, is given the symbol capital L. And the value of latent heat depends on the substance as well as the actual phase change. So there are different values for latent heat depending on whether your object is going from solid to liquid or liquid to solid. And the latent heat for when your object is going from solid to liquid and liquid to solid is called latent heat of fusion. Okay. And the latent heat involved when your object goes from liquid to gas and gas to liquid is called latent heat of vaporization. Okay, we've discussed earlier the meaning of the positive and negative signs in this equation. So positive sign is used when energy is transferred into the system, and that's when you have melting or boiling. And negative sign is used when the energy is transferred out of the system, and that's when the phase change is freezing or condensation. Now let us look at the process of turning ice into steam as shown in this graph. Okay, in this graph now we will combine both the equations that we've seen. Q is equal to mc delta T, the heat needed to change the temperature of an object, and Q is equal to ml, the heat needed to change the phase. Okay, so let's look at this graph. The y-axis is given in temperature. This is the temperature of water. And the x-axis is heat added to the water. So that means you have ice. that is initially at negative 40 degrees Celsius temperature. Okay. And then you heat up ice. Okay, so heat is added to ice so that ice is heated up. Okay. And this graph tells us how the temperature of ice changes as heat is added. Okay. So when heat is added to ice, notice that its temperature will increase. It goes from negative 40 degrees Celsius up to 0 degrees Celsius. 0 degrees Celsius is the melting temperature of ice. Melting temperature of ice. So at 0 degrees Celsius, ice starts to melt. Okay? And notice that while ice is melting, so of course, while ice is melting, you have water and still some ice that's being melted. And notice that while ice is melting, any heat that's added to the melting ice does not cause its temperature to change. So notice here that while you have two phases existing, water and ice, and while ice is being melted, the temperature stays constant at 0 degrees Celsius. It's not changing. Now, the temperature will stay at 0 degrees Celsius until all of the ice has melted into water. Okay? And once all of the ice have melted and there's only liquid water that exists, so you only have a liquid phase, then any heat that's added to the liquid water will cause the temperature of this liquid water to increase. But it will only increase up to a certain point. And that temperature is 100 degrees Celsius. Okay. And this 100 degrees Celsius is called the boiling temperature or the boiling point. So that's the boiling temperature of water, 100 degrees Celsius. Okay, so you can see here if you have a single phase, which is water, only liquid, any temperature added to this liquid water will cause its temperature to increase until its temperature reaches 100 degrees Celsius. At 100 degrees Celsius, water starts to boil. And so while your water is boiling, you have two phases that exist. You have the liquid water, and because your water is boiling, you have steam, the gaseous phase of water. And notice again, as you add heat to boiling water, okay, notice how the temperature of boiling water stays constant at 100 degrees Celsius. This shows us clearly that if you have two phases existing, liquid, water, and gas, steam, then any energy added to that system with two phases goes into converting one phase into the other. In this case, any heat added to water and steam goes into converting water into steam. And that is why the temperature does not change, because the added heat goes into the phase change conversion. Okay. Now, when all of the water has been converted to steam, that's this point here. When all of the water has been converted to steam, and you only have a single phase, which is the gaseous phase in the form of steam, any heat added to steam, to single gaseous phase steam, any heat added to steam will cause the temperature of the steam to change. It will increase the temperature of steam. Right. So in terms of equations, we can see here that when you only have a single phase, for example, ice, okay, the heat that's added to the system, to ice, will go into changing the temperature of ice. And the same is true when you only have water, okay, which is a single phase liquid that is existing. So any heat that you add while you only have water will go into increasing the temperature of water. So the equation here will be the same. Q is equal to mc delta T. It's the same equation, Q is equal to mc delta T. Likewise, when you only have steam, you only have gaseous phase, then the energy added to steam will go into changing the temperature of steam. So the heat added is equal to mc delta T. The heat added will change the temperature of steam. On the other hand, you can see here that if you have two phases existing at the same time, for example, water and ice, okay, then any heat added to water and ice goes into changing the phase of ice to water, meaning changing phase from solid to liquid. So in this part of the graph here, where you have two phases existing, solid ice and liquid water, the heat added goes into phase change, and that will be a positive ml if you're going from ice to water. Likewise, when you're boiling water and you have two phases, liquid and gas existing, water and steam, okay, the heat added to the boiling water in both liquid and gas phase goes into changing the phase of liquid water to gaseous steam. Okay, so we'll look at an example later on to see how we can combine Q is equal to mc delta T and Q is equal to ml in a problem. And you'll also have more practice during the workshop of interpreting this graph here and identifying which parts of the graph corresponds to Q is equal to mc delta T or Q is equal to ml. Okay, so for this lecture, let's look at this example to see when to use Q is equal to mc delta T and when to use Q is equal to ml. A steam burn is more dangerous than a burn from water at 100 degrees Celsius. Calculate the amount of heat energy transferred to the body as 1 gram of steam cools from 100 degrees Celsius to 36.5 degrees Celsius. And then we're given here the latent heat of vaporization for water, which is 22.6 times 10 to the 5 joules per kilogram, and the specific heat of water, which is 4,186 joules per kilogram per Kelvin. Okay, let's break down this scenario because there are two scenarios here. One scenario is when you have steam cooling down from 100 degrees Celsius to 36.5 degrees Celsius. And the other scenario is when you have water, just water at 100 degrees Celsius, cooling down to 36.5 degrees Celsius. Okay, so let's look at our graph again. So one scenario is that when you are starting with steam, whose temperature is at 100 degrees Celsius. Okay, so in the first scenario, this is your starting point. Right? And steam needs to condense. So there is a phase change. So there is a phase change from steam to water until all of the steam has been converted to water. So you start here from steam and you have this phase change. So you have both water and steam existing until all of the steam has been converted to water. Okay. Initially, the converted water is still at 100 degrees Celsius. All right. Once all of the steam has been converted to water, that water will start at the temperature of 100 degrees Celsius, and then the temperature of water needs to go down to match the temperature of the body or the skin. Okay? And the problem says that the body is at a temperature of 36.5 degrees Celsius, which is about here. Okay, right? So water, okay, initially starting at 100 degrees Celsius, needs to cool down to match the temperature of skin. Remember that if you have two objects that are in contact with each other and one object is hotter than the other, energy is transferred from the hot object to the cold object until both objects will have the same temperature, or until both objects are in thermal equilibrium. So this now will be the end point for the first scenario. So that's the starting point for the first scenario, and that's the end point for the first scenario. So the first scenario is you start with steam cooling down to water and cooling down to body temperature. Okay. The second scenario is when you start with just water at 100 degrees Celsius, boiling temperature. So that means you're starting from this point. So this is the starting point for the second scenario, where you start from boiling water at 100 degrees Celsius. And then that boiling water at 100 degrees Celsius will cool down to the temperature of the skin. So this will also be the end point for the second scenario. It will be the same as the end point of the first scenario. And the second scenario is you have water cooling down to body temperature. Okay, what we want to find is the total energy it takes to convert steam to water, and then water to cool down to body temperature, because that will be the total energy that the body will absorb from the steam that's on the skin. Okay, and then we also need to find the total energy it takes for water to cool down to body temperature, and then compare the two energies for us to determine which is more dangerous, steam burn or a boiling water burn. Okay, so first, let's calculate the energy released by 1 gram of steam. Okay. 1 gram is 0.001 kilograms of steam as it condenses to water on the skin. So steam is undergoing a phase change because it's going from gas phase to liquid phase. So the equation we need to use is equal to Q is equal to ml. And that will be latent heat of vaporization because you're going from steam to liquid. Okay, M is the mass of the object that's undergoing phase change. In this case, it's the mass of steam that's undergoing phase change. So that will be 0.001 kilograms. Okay, and then the latent heat of vaporization was given in the problem, which is 22.6 times 10 to the 5 joules per kilogram. And again, notice the consistency of units here. You have kilogram for the mass, will cancel out with the kilogram in the unit for latent heat of vaporization. So you're left with the unit of joules. Okay, and plugging in the numbers in your calculator, you have this energy, 2,260 joules of energy is released to the skin when steam condenses into water. Okay, now the condensed steam, which was just converted into water, is still at 100 degrees Celsius. Remember that water still needs to cool down to body temperature, 36.5 degrees Celsius. So energy is again released as hot water cools from 100 degrees Celsius to 36.5 degrees Celsius. But in this case, you only have a single phase, that is purely liquid water. And so the equation to use to solve for the amount of energy released when you change temperature from 100 degrees Celsius to 36.5 degrees Celsius is Q equals mc delta T. So M is the mass of the substance or the object whose temperature changes. In this case, it's the temperature of steam that changes from, it's the temperature of water, rather. It's the temperature of water that changes from 100 degrees Celsius to 36.5 degrees Celsius. And the assumption is all of the steam has been converted to water. So the mass of the water will be equal to the mass of the steam. So that will be 0.001 kilograms. Okay, and then you have the specific heat capacity of water. Okay, that's the specific heat capacity of the object whose temperature changes. So it's the specific heat capacity of water, which is given 4186 joules per kilogram per Kelvin. Okay, so delta T is the change in temperature of steam, which is the difference between these two temperatures. But now we convert it to Kelvin. But again, remember that you remember that when we're taking temperature difference, you can subtract the temperatures in Celsius and just change the unit to Kelvin, and that should be the correct change in temperature. So 63.5 Kelvin, and we use Kelvin so that it's consistent with the unit of the specific heat capacity, which uses Kelvin to the -1. And so if we analyze the units, the unit for temperature will cancel out. Okay, and also the unit for mass will cancel out. So we are left with the unit of joule, which is the unit for heat Q. And plugging in the numbers in your calculator, you will find the amount of heat released as hot water cools down on the skin is equal to 266 joules. Okay, so the total heat that's released to the skin when steam condenses and then water cools down to body temperature will just be the sum of these two energies. So that will be 2,260 joules plus 266 joules is equal to 2,526 joules. All right, so if in the second scenario, if we started from just water at 100 degrees Celsius cooling down to the body temperature at 36.5 degrees Celsius, how much heat would have been released to the skin? Yeah, in the second scenario, it will just be this amount of heat that's released to the skin. Okay, because you're already starting just from liquid water, so you don't have this heat, you don't have this additional heat that's being absorbed by the skin. Okay, so here we can see why steam is more dangerous than boiling water, because when you start with steam condensing into water and then cooling down on the body, you have this extra added heat that is released due to steam condensing into water on the skin. And just a final note here, you might be wondering, because we said energy is released from steam, okay? And so Q should be negative, right? Because energy is released from steam. But how come here the numbers are positive? Okay, these numbers here are the amount of energy that's absorbed by the skin. Okay, so these energies here are transferred to the skin. So whatever amount of energy is released from steam and from hot water is absorbed by skin. Okay, so you'll have this opposite sign relationship. So energy released by steam will be negative 2,260 joules and negative 266 joules. And so the total energy released by the steam and the water will be negative 2,526 joules. But the energy absorbed by the skin will be positive 2,260 joules when steam condenses, and the energy absorbed by the skin when hot water cools down is 266 joules. So the total energy absorbed by the skin will be positive 2,526 joules. Okay, so that wraps up lecture 16, where we learned about heat, specific heat capacity, and latent heat, and we looked at some problems on how to use specific heat capacity and latent heat. I've put up on stream some extra conceptual type questions, and so you can head on to stream and check out the post-class material just below the folder where you got this lecture slides and lecture videos from, and you will find PDFs there of extra conceptual problems about specific heat capacity. And then in the workshop, we will look at we will practice solving problems involving Q is equal to MC delta T and Q is equal to ML.